that, and now I want to pose you another scenario, something that you are actually a little bit familiar with. If you can remember, in your secondary school, you have dealt with finding area that is between two curves, that is bounded by a vertical line, x is equal to a, and another vertical line, x is equal to b. So if you were to apply what you have done in your secondary school, then area can be calculated in two ways. One is to split up this into small little chunks. Split up the areas into small little parts so that you can apply this. And please take note, we have mentioned it before, that this particular formula is very, very specific. It can only be used to find the area that is between the curve, the lower and upper limit that is spelled out by here, which has to be two vertical lines, and the axis. So if we want to apply that here, we got to break it up into parts. For example, I can find the area of this portion, and maybe I'm going to break this up into this part here where the curve is going to intersect the x-axis. Then I'll find the area of this. Then maybe I'll find the area of this. Then I'll minus away the area of this. And this is going to be very troublesome, right? So another way that we have learned in our secondary school is to use this formula. And the formula looks like this. So to find this area, it is going to be integrating from the lower limit, which is the leftmost point. So A to B. Then I'll take the expression for the curve that is on top, minus away the expression of the curve that is below. So this is also going to help us to find the area, but unlike previously, where we have to break it up into small little parts, this is extremely fast. But at the same time, I do know that for you guys to be applying this formula, some people just find it very confusing because if I were to do the more tedious way, I guess this is easy. Because we are applying this formula and we are just finding small little parts, then after that we will add them together or subtract some parts away. But how is this formula going to work? Let's take a look at it, and I want you to understand the key is not just going to be this formula, which is what a lot of people believe. They think that these two formulas are miracles, but it is definitely not. The thing that is the most important for areas and volume, it is your ability to improvise for different scenarios. The one that we've just done, this scenario here, when we are subjected to restrictions. The restrictions will be the area and volume that we have learned through standard shapes in our secondary school, and also these two formulas. So if I'm restricted to just this, how am I going to find this area? Let me give you a suggestion. Okay, we're going to do an improvisation here. How about we do a graphical transformation first? That means, okay, I'm not going to find specifically this particular area, but I'm going to simulate this area. So to simulate this area, let's do a transformation. I'm going to transform this curve up by, let's say, 100 units. So if I were to transform this up by 100 units, I'll be getting y is equal to fx plus 100. I'm going to do the same thing for this, which will give me, let's say, something that is like this. Y is equal to gx plus 100. And I believe that 100 is enough so that this entire region, now currently it is like partly on top and part of it is below, but I believe that 100 is enough for me to shift this entire region high up above the x-axis. So if let's say A is going to be here, let's say B is here, okay, A, B, that means this region, which is what I've just simulated, is actually going to produce for me the same area as this. Okay, and just in case you feel that, okay, what if 100 is not enough? Okay, there must be a numerical number that is going to be enough so that we can shift this and these two curves, right, high up above the x-axis such that the area is cleared from the x-axis. So let's say, okay, if 100 is not enough for you guys, right, how about we go for a plus C? Okay, C is, I'm telling you, it is going to be a number that is going to be enough to shift this entire region above. Which means that if I were to now subject myself to this, the area can be found by finding first this big area here, this big area, which is going to be integrating from A to B of fx plus C dx. Then I'll minus away this smaller area that is below, which is going to be integration from A to B of gx plus C dx. And now we are just trying to take one area minus another area, subjecting ourselves to the formula, which doesn't really help us to find a lot of cases other than something that is like this. So I'm applying here correctly, and I'm going to apply this for here. And we have learned for integration, we can put them together, put the two integrals together, provided that the lower and upper limits are the same, and it is happening here. So I can re-express this as AB of fx plus c, then minus away this, which is gx plus c, then dx, which means that the plus c and the plus c here, they will be minus of, which will leave me with a result that is integration from a to b of fx minus gx dx. Okay, and this explains to us why in our secondary school, we can just simply take the top curve minus the bottom curve, and this is regardless of the position of the region. That means the region can be entirely above the x-axis, the region can be partly above and partly below the x-axis, or the region can be entirely below the x-axis. It doesn't really matter, because we can always find that value that can help us to translate. In our secondary school, we don't learn that much about transformation, but now we do, to translate the region high enough above the x-axis so that we can apply this. And of course, in the exam, I will want you to just make use of this, because this is going to be fast. Quoting this to find the area that is bounded between two curves. Let's move on and take a look at another scenario.